Okay. Okay, you should see. Yeah. Okay, so I think I'll start. As Rajat already mentioned, we have today a joint presentation from me and Mirko, which is a PhD student that I'm tutoring. So I will present the more general part of the idea behind the system we have devised and implemented. And then I leave the stage, let's say, to Mirko that will give you a use case related to smart mobility and data retrieval, and also a quick demo. So I think we can start. Rajat already kindly introduced us, so I will not repeat the information you already gave. But just to mention that part of this work has been developed inside our the research group, the Latency research group, which is actually a inter-university research group. We was born in Bologna, University of Bologna, where we have faculty members and also PhD students that are working with us, but also, of course, in Urbino, where I am currently, we have people involved. And as Rajat partially mentioned, we have also people, like Mirko at the moment in Madrid. And we have also some PhD students that are working with us from the Macau Polytechnic University. So I will not go into that. Maybe Mirko can present a little bit. I don't know if there are some other information that you might add with respect to what Rajat already said.
Yes, just to say hello, everyone, and thank you for having us here. And yes, basically Rajat said everything. I can add only that my PhD thesis title is Decentralized System for the Protection and Portability of Personal Data. So I have an approach for blockchain also from the perspective of law, but I will not continue now, and I'll let the talk Stefano. Thank you.
Okay, thank you, Mirko. Okay, so again, before we start, I already mentioned the research group, and in particular, these are the people that have been involved, mainly involved in the topics we are going to present today. So, of course, me and Mirko, but also Gabriele D'Angelo and Luca Serena that are currently in Bologna. Okay, so as I mentioned at the beginning, actually this lecture is a sort of follow-up of my previous lecture that I did, I think 1 year ago, where basically I discussed issues related to how we can handle data in a decentralized way. So decentralized data management, basically, applied in the context of smart transportation systems. And in that case, I made a lot of discussions related to distributed ledgers and decentralized file systems. So I will recap a little bit something in order to make this talk independent from the other. But of course, if you want, you can have a reference for the past lecture, let's say. So in general, we are dealing with smart transportation systems. So we are talking about basically vehicles that move, and as you know, today, because of the sensors that are placed inside vehicles, you might have a lot of sense data. And of course, these are data that are usually produced in order to provide information related to the car, but not only. And the idea is that when you aggregate this data, you can create some kind of smart services when the data can be used in a different way with respect to how, why they have been generated. And so that's one of the interesting part of the idea of generating smart services and smart transportation. So basically, the idea is that you have this kind of personal data generated by each vehicle, or also other sensors, of course, that are placed in a road, but it is the aggregation of this data that gives a possibility to create some kind of smart services. So we need to find a way in order to handle and manage this personal data and make a sort of data storage which is shared among people that is interested in using this data. Of course, the typical option and currently how services are developed and deployed, the typical option is to resort to a sort of client-server architecture where you have a central server that collects all the data and use all these data that here are depicted with these boxes in order to make some kind of analysis and they can use in order to create the service, which is something good in some sense because of course it allows you to create all the services that we are using today. But from another point of view, this solution is not the best from certain perspective. Because it creates some issues that we should be aware of. The first issue is that you need to rely on the data controller, meaning that every time a user wants to use his own data, he has to ask to the server in order to retrieve them and exploit them. Okay, so you basically lose the sovereignty of your data. And this is something that you can accept, of course. It's the typical way of handling the data today in several services, but you might not agree with this. And another problem, because of course you can employ your data not just for your personal purpose, but maybe you want to share this data and maybe have a profit with this sharing activity. And so this is a simple example, but that should give you a hint why we want to avoid centralized that data management. And this is one problem, so related to how we can use and the data, who owns the data. Other problems relate to comes from the system point of view perspective. Of course, the use of a central system may create some problems related to the fact that the server is a single point of failure. Okay, and so it is very easy to, depending on how the server, of course, is handled, but the presence of the single point of failure means that you can attack the server and put it down with denial of service, for instance. And another issue is that usually this kind of systems are prone to censorship. Now, I won't go into the recent facts and the news and the Latvia weaving today, but there are examples in these days of countries that censored social networks and several systems that are organized as a classic client server system. So this is a good example, unfortunate, but it's a good example of why client server solution is easy to censor. Okay, so we would like to avoid this. There have been already examples, for instance, of having a decentralized Wikipedia that was censored in a given country some years ago, and you have the decentralized alternative that cannot be censored. And that's why, basically, we want to avoid this. So, as I said, in my previous lecture, I discussed this quite a bit. And if you want, you can here you can find a link. Of course, it is not clickable now for here, but then when we will give you the slides, you will be able to retrieve that lecture. But basically, if you want to avoid this kind of solutions, we need to refer to the centralized system. And in this case, we have two options, basically, simplifying a little bit. One is the use of decentralized file storage, meaning that you have several hosts that maintain some kind of information. Maybe it is replicated, but as you can see, every node here has a different data that it stores in its storage. The other option is the use of decentralized ledger technology, whereas basically, again, I'm simplifying a little bit, but you have a peer-to-peer system again, where each node maintains a full copy of the ledger. Okay, and this kind of solutions provide a lot of benefits in terms of high data availability, integrity, auditability, confidentiality, and the possibility to create smart contracts that allows you to automate and enforce processes. So why this? Of course, high data availability is obtained through replication. Here, in the case of the centralized ledger, is quite self-evident, I think, because every node has a complete copy of the whole ledger. So you have a system that allows you to retrieve the data using one of these nodes. In the case of centralized file storage, of course, we have some kind of a replication, because of course, maybe this data here is stored also in this node, and so through replication you have similarly data availability. It is not completely redundant to the state maintained by each node, but you have replication as well. I mentioned integrity and auditability. So basically, the idea is that when you have a data, you can check that the data has not been tampered or modified by someone else. So it's the original data you're retrieving. This is a feature offered by blockchains and decentralized ledgers in general. Again, I will not go into the details because it would require a lot of time with respect to the topic we are going to focus, which are a little bit higher level. But this is something that is provided by ledgers. Okay, so here you have that basically you cannot tamper one data, because otherwise you have all the copies, and because of how the system is organized, it's very difficult to do it. As concerning the decentralized file storages, here might create something that provides as well integrity and auditability. Because what you can do, of course, is when you have a data here, you can associate to this data digest, which is basically the result of the processing of the data through a hashing function. Okay, and what you can do is that you can take the digest and put it into a ledger. So once again, you employ a ledger together with the DFS. And the benefit of this is that you can have that these nodes maintain a complete storage of maybe data which is a large size, so videos, for instance, and images. And you have here in the ledger that you exploit together with the DFS. You have the hashes and the digest of this data that prove that the data has not been tampered at all. Of course, you can have also confidentiality, because basically what you can do is that you can encrypt the data. So the data is distributed and replicated in this node, but if you don't have the key to access and decode the data, you are not able to read the data as the plain text. Okay. And using a combination of all this, the fact that you can cipher the data and you can also employ other technologies such as the smart contracts. You can also create some mechanisms, some solution in order to automatize and be sure that some kind of processes can be enforced. So for instance, for example, you can create some kind of smart contracts that implement access control lists, such that only who is authorized to access the data is enabled to do it and sync with that. So at the end, the use of decentralized systems allows you to surmount all the issues I mentioned related to client-server system, and they do provide the possibility of having some additional feature that can be very interesting in several contexts and some domains. So basically, that was a little bit the summary of what I talk about in my past lecture. But now there's a question that we are trying to deal with today. And is how can I look up for data? Because when you look at this system, if you know that there is a data that is available here, you can retrieve it quite well. Okay, so you go to the ledger, you take the data, and that's it. If you are entitled to do it, of course. Similarly, in a decentralized file storage, if you know that there is a data that has a given content identifier, so an identifier that allows you to retrieve it, you can access the data. But this kind of solution do not allow you to create some kind of more complex queries. So for instance, let's say that I want to retrieve all the data that have been produced by sensors even in LA, for instance, related to humidity or the temperature. Okay. And the first question is how can I retrieve? Because of course I do not know where the sensors are placed. I don't know which are the ways to access and retrieve this data and where they're stored. I just want to know the temperatures sensed by some sensors in Los Angeles. And of course, we want to do this without introducing once again a central component, because of course I can add servers that maintains a sort of directory of all the data, and so I can ask him where I can try where I can find some kind of information, and then he can answer me. But as I said, I want to avoid a central component, and so I want to do it in a decentralized way. So here, and the rest of this first slide, I will refer to decentralized storage, but it's the same also if we employ a decentralized ledger. But the idea is that if you want to do this in a decentralized way, what I can do basically is to resort to some solutions that already existed since years now, that relates to the idea of resorting to some kind of peer-to-peer systems. And in this case, for instance, this kind of approaches can be implemented by resorting to distributed hash tables, for example. So the general idea here is that, is that given a data, we want to, what we can do here is that to add some kind of metadata that describe the data itself. So in this case, I'm describing the data using some kind of keywords, okay? So you have the data and you have here these keywords that describe, for instance, whether it has been produced, which kind of data you have, and whatever it was, okay? So you have keywords associated to data. And then now I won't go into the details and the boring stuff, but basically given a keyword, you can, of course, represent a keyword using some kind of bit string, okay? For instance, by using a sort of hashing function, something like that. And the thing is that you can add on top of or together with the centralized storage another decentralized system that maintains basically information related to this keywords. So in this case, what we are using here and what we suggest to use is a distributed hash table that is organized as a sort of FIFO queue. So here you have a pictorial representation. You can see a sort of cube in this case, so in three dimensions, where you have that each of these points here are nodes. Okay, logical nodes, or if you want, they can be also nodes hosts that in a peer-to-peer system. And as you can see, you have that each node has an identifier, which is a bit string. And as usual, in several DHTs, usually the key space of the nodes is the same. The ID space is the same of the key space. So the same identifier, a kind of identifier that you use to represent keywords. Okay, and as you can see here, you have links among these nodes that create a sort of overlay. So basically, this means that you have a node here, this 100, which is connected to these three nodes here that have a similar, let's say, identifier. So they basically differ from one bit. Okay, so you have this kind of logical overlay that actually it is a peer-to-peer systems where you have nodes, peers that are connected to other peers based on this IDs. And what you can do now is that you can assign to each node here of the peer-to-peer system a given set of keywords that are related to similar to this ID. Okay. So for instance, here I give you an example, a very simple, simplified example, of course. So you have here the keyword associated to a given bit string. So imagine that you have here the keyword key3. Through an hashing function, you have that the ID of this keyword is 100. So the node 100 is in charge of maintaining information about this keyword. And similarly for the other keywords. So keywords are distributed based on their ID that it is obtained by hashing their value. Okay, and they are maintained by the nodes that are similar or the same in this case identified. And now the interesting thing is that you can place this layer on top of the other one. And basically what you do is that this node that maintains information related to this keyword allows you to retrieve the data based on where they're stored. So for instance, here this node has information about key3, so it knows that you have a data here, and you have another data here, and another data here, and as you can see, another one here, which is different from the others. Okay. But basically, you have some information to retrieve this. And of course, every node does the same for his own keyword set that is maintained by that node. So that is pretty much the idea. Just to give you an example that relates also to the demo that Mirko is going to show. Imagine that you want to represent keywords related to locations. Okay, in this case, we can resort to a specific encoding, which is called open location code. So here you can see a map of the city where I'm in at the moment, which is Urbino. So you can see here it's the center of Urbino. Actually, it's a very beautiful town, so you can check it, and it deserves is worth of a visit. But apart from this, as you can see here, you have that the map is organized in a grid, and as you can see, every grid has its own code. Okay, so basically, every code here are the same prefix, and then the last part of the code that is different a little bit. And the nice thing is that if you focus and zoom on it, for instance, here this is a position where I currently placed. So here I'm talking to you guys from this place, which is the Collegio Raffaello, the city center. So as you can see here, if you look at this, you can see that this is the related code. And as you can see that it is a little bit longer than the other in this case, and the prefix is the same, but you had something more. So the nice thing is that the more you zoom in, and the longer the keyword that you have. And so basically, if you take a prefix, this means that you have a larger head. Why this is interesting? Because, for instance, let's say that you want to check some kind of information which is placed here. You are not able to do it, so basically you can enlarge a little bit using this code. By zooming out, that means that you can employ lower identifiers codes in order to enlarge the area. Okay, so I will avoid the technical things related to the fact that from this code you can transform it into bit string, but basically the process is that you have this kind of code, and by using some kind of hashing blah blah blah, you can obtain a related bit string. And as I said before, the mapping is made such a way that here you have the 2-bit string, and as you can see, if you have this area which is larger than of course the rectangles inside, you have a given bit string. And if you zoom a little bit, you have that the ones that are contained in this bit string are present, but you have other ones. So the more the ones you add, basically, and the more you are going to into a smaller area. Okay. Why this is useful? Because this allows you to do different kind of lookups. So what you can do is that, for instance, what is called a sort of bin search, in that you might want to look up for all and only the objects that are associated with a given keyword set. So you look maybe to some data that do have this kind of metadata associated. In this case, for instance, I made a search, an example, with looking with the keywords Wikipedia and Rome, for example, that allows me to have a given related bit string, and so I'm looking for specific data that do have this bit string. Or what I can do is do something that is called superset search, where basically I'm not interested only in the keywords that do have only these keywords, but I'm looking to data that do have those keywords, but maybe they can have others more. Okay, and so you can again enlarge a little bit the searching space. Okay. And so basically, if you start from here, okay, because you are looking for this 101 keyword, but then you are not happy with the information and the data that you have here, you can look at the neighbors of the hypercube. That's basically how this superset search is translated. You can ask him which keywords do you have and which data do you have associated to this, but you can also go to maybe to this one in order to add another keyword, something like that. And by looking to, I'm going here, you can add other keywords and other data. Okay. So that is the general idea. Basically, you have a decentralized system. On top of it, you have this kind of DHT-based peer-to-peer system that allows you to retrieve data that have associated some kind of keywords. Now, there is another question that remains open in this talk that I'm giving to you, which is how can we manage the decentralized lookup layer? Meaning that how can I be sure that people and peers, since we are in a peer-to-peer system, do follow the protocol, for instance, do respect all the rules, and basically also how can we provide incentives to participate? Because of course, when we are in a peer-to-peer and decentralized system, you need to provide some incentive to people to participate and give a contribution. And what we would like to do is to find an answer to these questions by looking to a solution that is preferably can be done where this can be done in an autonomous way and automatic way. Okay. And here is where smart contracts can enter and can join the whole story. So basically, what is a smart contract? Pretty sure a lot of you guys in the audience that are interested in blockchains do know what a smart contract is. But in the end, a smart contract is a program whose execution is performed in a distributed way and allows you to automatize and supervise exchange of whatever digital token and so on. And by using this smart contracts, you can create as what are called the Decentralized Autonomous Organization. So basically, a decentralized autonomous organization is a set of people that decide to participate and organize themselves. And all the protocols related to the interaction among these people is controlled by a smart contract or rather a set of smart contracts. This allows you to create some kind of decentralized services related to the governance, because you can implement here the smart contract voting system, for instance, that allows you to make decisions related to how can we evolve our system and other stuff. And also the rewarding, because you might have smart contracts that provide tokens to people that is participating in this system. Okay, so this is pretty much the general idea. Now we would like to put it in a context. So we will present now a use case that where all the things I said in a general way are described in a specific application. But now I'll leave the stage to Mirko. Maybe Mirko, you are going to present by yourself, so you want to switch the.
Yes, thank you. I will share the screen.
So I'll stop sharing, and so that you have.
Yes. Okay, so can you see the screen now?
Yeah.
So yeah, we decided to give a scenario for the application of this system. Of course, we focused on a vehicular use case. In particular, we wanted to show how the system can be used to detect road hazard while the vehicles, maybe autonomous vehicles, are going around the city. In particular, I just remind you that we have basically two main operations. The first operation is the insertion of data from a sensor or manually inserted in a decentralized system. And then the second operation is to index the data with the keywords, as Professor Ferretti said, into the hypercube system. So the first operation, we said, can be done in a decentralized file storage, as well as in a distributed ledger technology. In this case, we use IOTA as a DLT for the example, while for the decentralized file storage, we will use IPFS. Both of them, as you can see from this simple diagram, can be interchanged. And so because of course we focus on the hypercube DHT. I'm going to show you the use case. Repeat, it can be on IOTA or on a DFS, decentralized file storage. Once we operate the two main operations that are upload to the DLT and then upload to the hypercube DHT, we then want to retrieve this data. So we want to make one of the query that the professor has shown. So pin search or superset search. You find after the lecture, you can find the demo online on YouTube. And also the source code is open and it's on GitHub, and I invite you to take a look at it. So now you should see the video, I hope. And if you don't, please tell me. Yes, can you see it? Okay, I assume yes. But the first step that I wanted to show you is to how to install the software. It's really easy. You just need to use Docker and the Docker Compose. We have a part that is the server that are basically all the node in the hypercube. So first of all, you install the server. In this case, it's going to install 8 different Docker components, basically holding the hypercube DHT. Then we're going to install the client for interacting with this network. I repeat, you find this video on YouTube, so you can also check by yourself. Here we start the service. So as you can see, we start 8 services, all with different colors, just to keep an eye on which one is making a problem. And we're using a specific node for IPFS. So the data in this case is going to be uploaded to IPFS. And now in this part of the video, we'll show you how to run the client. The client is a simple command line interface, indeed, but allows you to interact with the network. So it's this one. We're going to see later how it works. Now we focus on the scenario. The scenario is really simple. As you can see, it's a beautiful graphical interface, but just for showing you how it works, it is a Manhattan Square region, a map. In here, we can see that there is a road hazard. So we imagine an autonomous vehicle that wants to communicate this road hazard and send the first message to the DLT. So the message will arrive to a node in the DLT that will append a new transaction. And so the second message from the vehicle will be to the hypercube, telling to the hypercube network to point to this new message in such a way that people can then query this new keyword in order to find this road hazard. And so the result of this will be that, again, in the map, there are many vehicles that query for road hazard, other people that indicate this road hazard. And so everyone will use the system in 2 different perspectives, but at the same time. As I said before, it can be a DLT where we store data, or it can be a decentralized file storage. For this, in this demo, we will see IPFS as a decentralized file storage. Later, we will see how the application will run on IOTA performed. So, coming back to the client, so we have now a network of 8 node app, and we want to insert new data to a new keyword to the DHT. So first of all, we have this test txt that is going to be inserted into IPFS. Then we want to select a keyword. So how it is represented in the DHT. In particular, we have a range from 0 to 7, just because instead of using a binary, we use directly the representation in 10 decimal places. So if we select the keyword 5, we're going to interact with this node in the hypercube that holds these kind of keywords. And so in this case, we just click enter, and the data will be stored in IPFS, and the keyword will be stored in the hypercube. Now we want to get the data from the hypercube. So we are assuming this is another keyword, another vehicle that is going to search for keyword 5, because maybe keyword 5 is a specific region, and it will obtain this index, which is the index for finding the data in IPFS. So I repeat, the vehicle made a query to the hypercube using the keyword 5. The result is that index. We can use this index to get the actual data. The implementation webmaint will download this data into a local folder. The local folder will have a TXT, just showing you the object that we with this index. That is simply hello world. Finally, we have the final query, which is the superset search. So we are going to find the objects with keywords that are not only 5, but maybe also 6, 7, because they're near. As you can see, we find another index. So we find the previous one, which is this first one, and then another one. We're going, in this case, to take a look also at this file. That is, I repeat, this stored in IPFS. As you can see, we obtained from the superset search more data, more files, and this is the final output of the second file. So all of this you can test it yourself by downloading the source code, or you can just watch the demo on YouTube. We performed a series of similar tasks, but in sequence. And of course, we simulated much more vehicles, up to 100 vehicles interacting with the IOTA DLT instead of IPFS. These are the results of the latency for communicating with an IOTA node. As you can see, the average is around 3 seconds for inserting data to the DLT. In this case, interacting with the node that was deployed by ourselves. On the right, instead, we interacted with a node that was publicly available for interacting with the ledger. Then we focused on executing the same number of requests to the hypercube. And so these are the results. On the left, we find the insert latencies around 2 seconds that increment slightly with the increments of the hypercube dimension. So hypercube dimension 3 means that is, of course, hypercube, a network that is smaller than the hypercube 6. At the center, we find the latency for querying with the pin search. Also, in this case, we have a latency average around 1 second. And on the right, the superset search, which is higher than the pin search because it has to search for more objects. Indeed, we then have the number of ops. These results shows that the implementation of the system was correct, at least from the theoretical perspective. So we know that theoretically the number of ops that are the request connections made from one hypercube node to another hypercube node in the network to reach for an object. We know that they have to be on the order of the logarithm of the number of nodes. And the results in these plots shows that we follow what is theoretically, what should be theoretically possible with the latency. At last, we have the latency in the case of the retrieval of data from the DLT. As we can see, this is one of the most problematic one because of the high latency, but still feasible in a scenario of vehicular use case. In conclusion, we presented the Hypercube DHT, a decentralized system that manages keyword-based queries for content stored in distributed ledger technologies or decentralized file systems. It presents an efficient trade-off between memory space and response time. We presented a way to govern this system using a decentralized autonomous organization and an ERC20 token to incentive the nodes to operate. From our results, we found out that it is a viable strategy for mass transportation services. So I'd like to thank you. You'll find the references, and please, we are looking for your questions.
Thank you, Mirko and Stefano. Any questions from the attendees? I don't see any question in the chat box. So if you have any questions, please deposit them in the chat box. I guess not. So are you publishing this result in any papers?
Yeah, as Mirko mentioned at the beginning, at the end of the presentation, we published just published a paper into a journal which is called IET Networks. Okay, yeah, thank you, Mirko. So you have here the link. Actually, it is open access, so you can retrieve it and read it. So yeah, so that basically is the general description of what we presented today, basically.
And you mentioned you use IOTA. Does it also work with non-IOTA type implementations?
Pardon? Sorry?
So you mentioned that you implemented this in IOTA, right?
Yeah. We implemented. We used IOTA as a ledger to where the data are stored, but we are used to use it because it's a quite nice technical solution to where you can just store data. Of course, it can be applied also to other DHTs and also to other decentralized file systems such as IPFS, for instance. But yeah, the IOTA was the reference DLT for this kind of actually for the tests, basically. I see there's something.
There's a question in the chat box from Chris. Could you elaborate on possible smart city transportation applications and perhaps proof of location?
Yeah, I mean, basically, that's one of the possibilities. Now, proof of location is very good idea. Maybe I don't know, Mirko, if there's some solution now, but it might be, I think, a good application to think that. As related to smart city transportation, of course, as I mentioned, for instance, let's say that I want to retrieve some kind of information related to parking, I don't know, near the Grove Center in LA. Basically, I might try to look there, but I cannot find information. I can just enlarge a little bit, maybe in the area of near in Beverly Hills and so on, and enlarge. And the nice thing is that you do not have to resort to a central discovery mechanism as a service, but you can employ information that is related to what is stored in the DLT. So every kind of information that comes from sensors or information that is stored there, so something related to maps and something like that, geographical information systems, for instance, can be
If
some.
I may,
Yeah.
I also wanted to add that for instance, there are some application of the proof of location in Ethereum, but you need to know, for instance, the address of a smart contract to know to reach that proof of location, or otherwise you need a database that indexes all these proof of location. In this case, what the system we propose is to have an efficient way and also decentralized to index exactly that address that refers to the proof of location. So we are more focused on the efficiency to access this data, more on what data we are creating.
We have another question from our colleague Xiaoling Zhu. Thanks for the great presentation. I have a question related to the data insert and retrieve. From what you mentioned, these times are in the level of seconds. Will this be suitable for a smart city application?
Well, this is another good question, because of course it depends on the kind of application. It depends if this kind of responsiveness, let's say, is sufficient for you. In the case of IOTA, for example, we, as I mentioned, we used it as a reference. But in the end, since you need to have when you insert the data into this ledger, you need to perform some kind of proof of work, which is not as complicated as in Bitcoin, but still it requires some time. So in this case, of course, if real time is something that is related to the application, so maybe that is not the kind of DLT you want to use. Now there are other DLTs that should provide higher responsiveness levels, so basically lower latencies. But you need to tune, and basically you need to select the kind of distributed ledgers that answer your needs. Of course, the faster the insertion, maybe you might have on the other end other problems related to the security in some sense in certain cases, because maybe you avoid the fact that you're using a proof of work or things like that. So it really depends on the application. I understand that seconds might not be a good time in order to insert data. I don't know, Mirko, if you have
on this yeah, on this chart that you're showing, what's on the y-axis? Is it number of nodes?
Yeah, number of nodes that it is latency.
Okay.
Histogram. So yeah, I think I don't have anything more to add to Stefano's reply. So, thank you.
Oh, thank you.
Okay. Well, we don't have any more questions and we're top of the hour. Thank you both, Mirko and Stefano.
Thank you.
Video of this
Thank you.
The video of this presentation will be available in our mobile website. Give us a week or so.
Okay.
And thank you all for attending.
Thank you all. Take care. Bye-bye.
Thank you all. Bye.
Bye.